Welcome everybody. So it's a special pleasure today to have Mathieu Anel from the Carnegie Mellon University. So it's a special pleasure because Mathieu was one of the pillars of the last program we had a few years ago. Mathieu will talk about the enveloping infinity topos of a presheaf one topos. Please, Mathieu.
Thank you, Joachim. So it's a real pleasure to be back in Barcelona, if only virtually. But it's very nice to see all of you again. So thank you very much for the invitation. So I'm hoping to be among you next year for the real thing. I'm going to talk about a sort of a problem of infinity topos theory. And so I'm going to start with a diagram. Oh, I don't see the diagram anymore. So let me set my things better. Okay. So I'm going to explain all this in more detail in a minute, but infinity topos theory is an enhancement of sets by infinity groupoids. And we're going to replace presheaves or diagrams in sets by presheaves of infinity groupoids. And so it seems natural to believe that in the same way that the category of infinity groupoid is some kind of replacement or envelope of set, and technically it's going to be the so-called enveloping infinity topos. I'm going to recall the definition in a moment. So it's only natural to think that if the same thing are going to work for diagrams, is that if I take some diagrams of sets and I try to compute the envelope, then it's only going to be diagrams of infinity groupoids over the same category. So these envelopes, they have universal property. I'm going to recall that. And they can be thought as a completion for homotopy colimit. So it's a relative completion, meaning we're going to keep some colimit existing in those categories, and we're going to add some others freely. And so it's only natural to believe that this diagram commute. But the surprise, at least it was a surprise for me, and I discovered this only last year. The truth is that, in fact, this does not commute. So so in a way to say that is that if we take the infinity envelope of an infinity topos of a presheaf category, it need not be the presheaf of infinity groupoid over the same category. So this is the problem that I'm going to explain today, and I'm going to provide criteria on the category C for when this is the case, that the two objects coincide. But let me place this in the context of a very concrete example. We're going to look at our favorite presheaf category, which is simplicial sets. And so this problem that the envelope of the enveloping infinity topos of a presheaf one topos need not be the higher presheaf, it has immediately the question for simplicial sets, whereas, I mean, is the envelope of simplicial sets simplicial spaces? And I mean, I'm sure all of you are ready to say that, yes, of course it is. Because if it is not, then something is very wrong. Because if the envelope is not simplicial sets, if simplicial sets is not produced, if simplicial spaces is not produced universally from simplicial sets, then we might have to change a number of things in our practice of higher category theory. And so fortunately, it happened that the envelope of simplicial sets is indeed simplicial spaces, but this is not an easy proof. It's not a formal consequence. So we're going to go through the proof, and we're going to see that the proof requires some the introduction of some ideas. So that's the goal for today, is to prove that the envelope of simplicial sets is indeed simplicial spaces. So here is the plan. I'm going to recall what is an enveloping infinity topos. I'm going to explain why the envelope of a presheaf one category is not a presheaf infinity category. And then we're gonna find conditions over which this is true, and then we're gonna move back to simplicial sets. So the notion of infinity topos has become one of the central notions of higher category theory. So the infinity topoi are to topoi what groupoids are to sets. And we're going to see that in a definition. And so for an introduction to infinity topoi, I'm going to make a little commercial for myself here. We wrote a paper with André Joyal, which is available on my website, and which is part of a collection of papers recently published by myself at Cambridge University Press. So in this book, New Spaces in Mathematics and Physics. So let me recall the definition of a one topos, because we're going to see that we're going to need that in the end. So one topos is a presentable category having some good behavior of coproducts and equivalence relations. And the good behavior is that the coproducts and equivalence relations are so-called universal and effective, so or disjoint for the coproduct, which means that we have those equivalents of categories here. The slice category over a coproduct is the product of the slice category, and the slice category over the quotient of an equivalence relation is the limit of the categories here. So I'm not going to explain more those definitions because we're not going to need them. More concretely, a topos is a co-continuous and left exact localization of a presheaf category. And similarly, we can define infinity topos. And the definition is interestingly simpler because we only have a single axiom now, which concern arbitrary colimits. So we don't have the dichotomy between sums and quotients of equivalence relations. Now the condition of being universal and effective has to work for arbitrary small colimits. And again, more concretely, infinity topoi can be characterized as co-continuous and left exact localizations of higher presheafs. Now they are presheafs with value in the infinity category of infinity groupoids. So there's a lot of similarities between one topoi and infinity topoi. And in fact, these similarities are rooted in a very close relationship that sets and infinity groupoids have. So as it happened, the language of Martin-Löf type theory, which has been invented for sets, has been discovered about 10 years ago to be quite a comprehensive language also for infinity groupoids. And so, so this legitimates the idea that somehow sets and infinity groupoids are two instances of the same formal language. And so similarly, it's a bit of a stretch, but we can say that somehow one topoi and infinity topoi are also kind of the same thing. And most features that exist in the same way that most features of sets can be generalized to infinity groupoids, most feature of one topoi can be generalized to infinity topoi. But there is one new thing with infinity topoi that does not have any equivalent in the world of one topoi. It's the so-called infinitely connected maps. So we're going to need them for a counterexample later. So I'm going to explain a bit what they are. So in an infinity topos, every map has a Postnikov tower. So this is a generalization of the Postnikov tower of an object in homotopy theory. And if you assume that the object Y is the terminal object, this is just the Postnikov tower of the object X. And so these are the truncations of the homotopy levels. And on a map, this is done fiber-wise. And so a map is called n-connected if the end stage of the Postnikov tower is equivalent to the base of the map. And the map is called infinitely connected if all the PNs are equivalent to the base. So the whole tower is constant. So in the category of spaces, of course, there's no, the only examples of infinitely connected maps are the maps that are isomorphism themselves. But there exists infinity topoi with non-trivial infinity connected maps. So it's not a necessary condition. A map can have a trivial Postnikov tower without being an equivalence. So a kind of example is given in parametrized spectra. And if I have time, I might give another kind of example. So a little bit of vocabulary. If all infinitely connected maps coincide with the class of, if the class of infinitely connected map coincide with the class of equivalences, the topos is called hypercomplete. And an example is a presheaf topos. So I recall that this is functors from my category C up into the infinity category of groupoids. So any presheaf category is hypercomplete because S is, and so the same is going to be true for diagrams. And any infinity topos can be hypercomplete, and by inverting all infinitely connected maps. And this is a localization of our topos, and it is co-continuous and left exact. So this is another topos. Okay, we're going to use that later in the talk. So let me review now the notion of envelope. So if you're not so familiar with infinity categories, it helps to understand the enveloping infinity topos as a generalization of the one topos. That should be a one. I should have put a one here. So we're going to generalize the envelope infinity topos is going to generalize the category of sheaves over a topological space or over a locale. And the formal definition of this envelope is as a right adjoint to some truncation operation. So if I have an arbitrary topos, I can look at the subterminal objects and that define a locale. And a fancy word for a subterminal object is -1 truncated objects. And I can do the same with an infinity topos. I can take the 0 truncated objects and I get an ordinary 1 topos out of my infinity topos. And so the enveloping functor are going to be adjoint to those truncation. So if I have a topological space, I can take the envelope 1 topos of my topological space, and this is going to be sheaves over the locale. I'm going to recall the definition in the next slide. And in the same way, the enveloping infinity topos is an operation that takes a 1 topos and constructs an infinity topos. And because those functors are fully faithful here, we recover we can recover the original frame. The original frame becomes the subterminal object of our 1 topos here, and the original 1 topos that we start with becomes exactly the 0 truncated object of its infinity envelope. So how do we compute the infinity envelope? So let's recall how to construct the 1 envelope first, or the 0 envelope, I should say. So if I have a frame, I define the sheaves as a subcategory of contravariant functors with value in sets, which satisfy the so-called sheaf condition. And the sheaf condition is this one. So for any object U and any covering family of U, the value at U has to be the limit of this diagram. So I'm assuming you all know that. And so the definition of the infinity envelope is going to be exactly the same, but we just need to replace the small diagram that we had before now by a full simplicial diagram. And we need to index the higher sheaf conditions by covering families. So this does not change. And so it's possible, it's easy enough to prove that this construction provides the left adjoint that we wanted before. So things are looking good. I mean, the envelope always exists, but there's still this problem that I mentioned, that the envelope of a presheaf category need not be the higher presheaf category. And so I don't know if you find it disturbing. I mean, I couldn't believe it when I first noticed it, but because it seems bizarre, because if it is not the higher presheaf, what is it? It has to be something simple enough, because this category are so simple. We're going to see that this is actually quite involved. And now let me mention a result that if we don't go up to infinity, but we stop with n truncated groupoids, with n groupoids, then it is true that the envelope of a presheaf is always the presheaf in n groupoids. So the thing that is bizarre only happens at infinity. And I guess somehow it's not so surprising, because I mean, we're used to surprises. When we push something up to infinity, we know that some bizarre behavior can happen. And so this is life at infinity. So let me mention a counterexample to this presheaf envelope thing. So the counterexample is actually pretty old. Is inside those papers of Duggar, Hollander, Isaacsen, and the notes of Resk in Topoid, on homotopy Topoid. But the thing is, it's kind of hidden inside. It's not stated as such. It's not stated as a counterexample for this property of enveloping topos. What they do in this paper is that they try to construct non-trivial examples of those infinitely connected maps. And I owe to Jonas Frey the remark that this construction of infinitely connected map is actually done in the enveloping infinity topos of a presheaf 1 topos. And so this is going to prove that there exists a non-trivial infinity connected map in the envelope. And so the envelope cannot be a presheaf category. So I'm not sure how much time I'm going to have to talk a bit about this example, because there would be, I mean, I could give a whole talk on just this kind of example here. So is there a question? Sorry.
Yeah, if you hypercomplete this infinity topos, will you get what you expected?
Yes. Yes.
Ah, okay.
Exactly. So the higher presheaf, I could have said that earlier. Thank you. So the higher presheaf is going to be the hypercompletion of the envelope. So we're going to see that a bit later. So let me say just a quick word on this example. And if I have time, I'll go deeper into it. So here is the poset. We're going to look at presheaves over this poset. So this is not the way they present it. They present it as sheaves over some locale, but as it happened, the locale is actually presheaves over this kind. And so they prove that the envelope of presheaves of sets over this poset as a non-trivial infinity connected object. And this involves some relationship with a stable homotopy theory. Anyway, I'll come back to this, hopefully. So the envelope of presheaves need not be presheaves. And this is a bit of a problem, because then the envelope of a category of sheaves need not be the category of higher sheaves, because if it is already false for presheaves, a fortiori is going to be false for sheaves. And so this means that we cannot use a presentation of our 1 topos by a site to compute the envelope. So that's a bit distressing. But fortunately, from an abstract point of view, the situation is always as an answer, because if the diagram category, the indexing category of a presheaf has finite limits, then everything is fine. Then it's easy to see that the envelope is indeed the higher presheaf. And the proof has actually, the proof is there, essentially 4 lines. So let me skip over the proof because I had prepared some slides to talk about the proof, but I think I'm going to jump over to for reason of time. So anyway, so if C has finite limit, everything is okay. And so we can, the thing is, we can always present a 1 topos using a site with finite limits. So that's good, because that means that we can still use the site technology to compute the envelope. We need only to consider a site with finite limits. And we can prove that this is compatible with the topology. So if the site is Lex, then the higher envelope is indeed the naive sheaves for the site. So, but this is not exactly satisfying. It's satisfying in theory, but not in practice. And the problem is that there's a lot of 1 topoi that are not naturally presented by means of a Lex category. and that's the G sets. So certainly we don't want to try to present G set by means of a topology on the Lex category. That would be overkilling the thing. And we have simplicial sets also, and cubical sets. If we have a Lovier theory, we can look at the classifier of flat algebras. Yeah, I'm not going to talk about the last example. But certainly in those three examples, it would be bizarre to replace, since these are presheaf categories, it would be bizarre to force a presentation of those presheaf categories by means of a topology on the Lex category. It's possible, but it's actually difficult, because what would be exactly the Lex category generating those guys? It can be quite involved to come up with one of them. And so we would prefer to keep working with just actions of a group, or a diagram indexed by delta, or by some cubical category. And so the question is still around what is the envelope of those guys? Are they what we expect them to be? Because those categories are so simple. I mean, I mentioned simplicial sets, but can you imagine that if the envelope of G sets is not G spaces? That would be horrible. Something would be very wrong in homotopy theory there. And so let's try to see. So we're gonna study the envelope of those three examples. So we need to understand two questions: why something is wrong, and when it is actually right. So that's the goal. How much time am I doing on time? I think I'm good. So let me jump over some slides here. I had some remark about flat functors, but I'm skipping over it. So here is a way to understand what is the problem. So we start with a category. It's a one category. And then we look at presheaves of sets. And of course, the Yoneda embedding is dense. Every presheaf of set is a colimit of representable presheaf. Now, the envelope of our topos is, by construction, is also generated by the discrete object. It's possible to prove that every object in the envelope is a colimit of a discrete object. And the problem is that if we compose two dense functor, it is false that it is a dense functor automatically. And so the thing that's going to happen is that our representable presheaf are not going to be generators for the envelope anymore. So that's a scandal, but we'll see why this is true. So not all objects in the envelopes are colimit of representable. And the problem is because this inclusion here, it may be dense, but it does not preserve the colimits. And so if I have a discrete object, if I have a discrete presheaf, which is a colimit of representable, it may not be anymore a colimit of representable in the envelope infinity topos. So the problem actually is not so much with the guys in the envelope. The problem is with the discrete presheaps. And that somehow the Yoneda embedding is not dense anymore if we look at it inside. Oops, sorry. If we look at it inside the envelope, if we compute colimits inside the enveloping topos, then not every discrete presheaf is a colimit of representable. So to understand the problem, let's introduce this map. So there should be an F here. So F is a discrete presheaf. And so I consider its category of element, and I consider the canonical colimit of its element. But now I'm computing this colimit in the envelope. And so this map need not be an isomorphism anymore. And so I'm going to say that my presheaf is good if the map is an isomorphism. And of course, any representable factor is good, because in this case, this colimit has a terminal object. And so it's just the value of the terminal object. So good objects do exist. And so now here is the main theorem. So we can prove that all those maps are infinitely connected in the envelope. And so this is why we don't see this phenomena where we truncate the groupoid. If we work only with n groupoids, then all those, the analog of those maps are going to be equivalences. Now we can prove that the hypercompletion of the envelope is actually generated by those maps. And we can deduce that the hypercompletion of the envelope is the actual higher presheaf category. And so putting all those results together, we get a criteria for when the envelope of a one presheaf is the higher presheaf. It's necessary and sufficient that all discrete presheafs are good. And so this is what we're going to use to work on to solve our problem for simplicial sets. So the envelope of simplicial set is indeed the topos of simplicial spaces. And here is the proof. Well, we have to show that all simplicial sets are good, according to the theorem. So all we know so far is that the representable objects in the envelope are good. So we need a result to construct more good objects from good objects. And so here it is. So good objects, the subcategory of good objects in the envelope is stable by the following operations. So first of all, we have what I call the Giraud colimits, which are the colimits involved in the definition of a one topos. So these are the coproduct and the quotients by equivalence relations. So if I have a coproduct of good object, it is a good object. If I have an equivalence relation within good object, then the quotient is again a good object. A particular case of this equivalence relation property, which is nice, is push out along monomorphisms. And so why are a good object stable by this property, because these are exactly colimits which are preserved by the inclusions into the envelope. So this inclusion doesn't preserve arbitrary colimits, but it preserves some colimits. And it's easy to see that it preserves exactly the colimits of this proposition. And if we can, all the objects that we can construct from representable using those kind of colimits, they're gonna be good. So let's go back to the proof that all simplicial sets are good. Well, you may have already an idea on how it's going to work. So we know that all the representables are good. And now, if we prove that all the boundary of representable are good, then we're almost finished. And so we're going to do that. And so we're going to do it by induction, using the push-out along mono thing. So first, I look at the boundary of delta 1. So this is just a coproduct. So a coproduct of representable. So this is good. And now I need to construct the boundary of an arbitrary n simplex. And so this is a pasting of n-1 simplices along n-2 simplices. So these are push-outs along mono. And only the last face is no longer pasted along an n-2 face, but along the boundary of an n-1 face. But by induction hypothesis, this is going to be good. And so I can construct all my boundary. Maybe I should make a little diagram here. So let's say I want to construct the boundary of my 2 simplex. So I start with this guy, which is good. And then I'm gluing another delta 1 along a delta 0. So that's a push out along a mono of good object. So that's it's this push out, and all the objects are good, and the maps are mono. I mean, it's enough that only one map is a mono. And so my guy is good here. And then I need to glue the last face. And this is a push out along the boundary of a delta 1. So it is good also. So all the boundary of simplices are good. All the simplices are good. And so now it's easy to finish the proof, because an arbitrary simplicial set is an iterated push out of those maps. So all simplicial sets are good. And so this proved that this eta map that I define for simplicial sets, it's always an equivalence. And so the envelope of simplicial set is indeed simplicial spaces. And so homotopy theory and higher category theory are safe. Now let's play with another example. How about G sets? Well, we need to prove that all G sets are good. And well, it's easy enough. So the generator is G acting on itself. So it is good because it's the representable fractal. And then it's enough to prove that the orbits of G are good. And then every G set is a coproduct of orbits. So we know that coproducts of good objects are good. So we need to prove that the orbit is good. And we're going to write our orbit as a quotient of an equivalence relation. And this equivalence relation, it's an equivalent relation in coproduct of copies of G. So this is a good equivalence relation, and so its quotient is good. And then the proof is finished by using that any G set is a coproduct of orbits. So we say the envelope of G set is indeed G spaces, and all is for the best. So the proof is a bit more involved, but we can prove also that the envelope of cubical sets is indeed cubical spaces. So there's many cubical categories. I haven't tried with all of them, but in the case of the so-called Dedekind cube, then it's possible to prove that all cubical sets are good. And hopefully all this will be written soon in a paper. And I think I'm gonna stop here for a few questions. I have a bit more slides about this counterexample of the Gerlander, Isaacson, and Resk that I can continue, but maybe it's a good time to take some questions.
Okay, thanks a lot, Mathieu. So questions. Claudia.
What's a counterexample where this doesn't work?
Okay, I'm going to answer this question maybe after other questions.
No, but I mean, is there an easier one? Something that would be...
well, constructing infinitely connected objects is never easy somehow. So I mean, you might find it easy, but... That's
a logical thing. So things like theta n.
Yeah, I'm gonna show the counterexample, but maybe we should answer questions about
categories. Other categories we would be interested in from infinity categories like theta n or these types of things. They should all, in theory, work.
There shouldn't be a problem with that. I think all the categories that are somehow combinatorial in a certain sense and involving some finite combinatorics, I think they should be safe. Yeah, let me come back to this remark in 5 minutes.
Other questions? Well, then maybe it's time to come back to
Tanya, other question.
Yes, I had a question. I hope my mic is working. Sometimes that problem.
Yep.
Okay, great. So actually, until your example of G sets, I somehow started to feel that what you were getting at was that your small one category had to have the homotopy type of a set, or because all the examples that you gave, and even the counter example that you gave, was something which is not a homotopy type of a set. But the examples of where this happens were all homotopy types of a set, right?
I'm not sure what you mean by homotopy type of a set.
The nerve of the category itself is weakly equivalent to.
No, because in a counterexample, the nerve of the category is contractible.
Ah, okay.
In the J category.
Okay, okay.
So no, it's not as simple.
Okay.
And but you can write.
Oh, sorry. No. I'm not sure if that's exactly what I meant. No, sorry.
But nonetheless, I think your intuition is a good one, because something like this is happening. I mean, some category have kind of a secret shape which is not contractible, and but it's not the naive shape, it's not the naive realization in infinity groupoids. It's the realization of the category in its own envelope. It's the the co-limit of all the diagram of representable in the enveloping topos. This may not be the terminal object. So it's not a necessary and sufficient condition for a category to be good and for the envelope to be the presheaves, but it's a necessary condition. That now that we know that the Yoneda, where am I? So now that we know that the Yoneda embedding here is no longer a generator, the co-limit of this diagram need not be the terminal object anymore. And so that's an obstruction. That's an obstruction. It's one of the particular cases of
yeah, exactly. I understand. Yes,
when F is the terminal zero presheaf, this map is some infinitely connected object.
Yeah. Yes. So, but as you said, that doesn't necessarily follow, nor does it imply that.
No, it's not sufficient. You can have categories such that for the terminal object eta F is an equivalence, but nonetheless, it's not an equivalence for all discrete presheaves. Actually, a necessary and sufficient condition is that this map is an equivalence for all finite limits of representable. Because the finite limits of representable, they're going to control everything.
Any other questions before we come back to Claudia's question?
I have one little question.
Please.
You were talking about these categories where there were morphisms which were infinity connected, but not isomorphisms. And then there was this counterexample, if I got it correctly, there was this counterexample which was constructed to find such a category, and that also worked to give you an example for your thing.
Yes.
The categories that sort of people are interested in, do they also have this property of being hypercomplete? So is it maybe the takeaway that we should not only envelop but also hypercomplete in the end, or?
So you could definitely do that. I mean, it's possible to restrict to infinity topos which are hypercomplete, and doing that simplifies a lot of things. And somehow all the bizarre features of infinity topos kind of disappear. And then the theory is really, really close to the one topos theory. But somehow it's too close to one topos theory because nothing is new anymore. And so for me, the interesting thing about infinity topos is precisely those infinity connected objects and the non-hypercomplete infinity topos. This is where something is happening, and this is where there's research to be done, because we want to tame those infinity connected objects and infinity connected maps. And so with André, we've been working for years trying to tame the beast of non-hypercomplete topos.
Okay, thank you.
So maybe it's time to go to the example in more detail. Okay, so this is the bizarre guy. It's this poset. So let me say something about this poset to understand where this poset is coming from. I mean, some of you might recognize this poset because it's a poset used for many counterexamples. So if I look at this part of the poset, I'm forgetting the higher part. Then I have an S0. If I look at this part of the poset and I take its realization, I get an S1. because this is the realization of the part of the greater lower than 1. And if I take this part, I have an S2, and etc. So this is the logic behind this poset. It's the combinatorics of S infinity and all the hemispheres of S infinity. So a good name for the poset could be S infinity. And okay, so this is the idea: is that we're gonna work on spheres, and then we're gonna push the dimension of spheres up to infinity, and at the limit we're gonna find some bizarre phenomena. Oh, by the way, this is why the poset is contractible, because it's S infinity. So I take its realization in infinity groupoids. S infinity is contractible in infinity groupoids. But somehow S infinity is not always contractible in arbitrary infinity topoi. That's kind of the idea here. Of course, we would need a definition of S infinity, but you can take S infinity as the colimit of this diagram, and it need not be contractible always. I have a poset, and so I can look at the frame of the presheaf frame on my poset, which are just presheafs with value in 0, 1. And this is the frame, and it's a frame corresponding to the Alexandrov topology of this poset. So it's a nice space. And now here is an explicit description of the frame. So we're going to add a terminal object, an initial object, and intermediate objects here, which are both the join and the meet of the previous and preceding pairs. So in our poset, all the squares are by Cartesian somehow. I mean, it's a bit fancy to talk about Cartesian square in a poset, but that's what it is. And so this is our frame. And so now we can compute sheaves over this guy. And so a sheaf is going to be a diagram like this. So the direction of arrows has changed now. And so I'm going to have some objects AI, some BI corresponding to the object of the original poset J. And then I have this middle object. And at the end, I have the terminal object because it's a sheaf. And the sheaf condition has to do, with the covering condition of the poset, which are given by those co-Cartesian squares here. And so each of those co-Cartesian squares, the level of sheaves, has to be sent into a Cartesian square. Hence this relation. So, and the definition of sheaf is the same for a sheaf of sets or for a sheaf of infinity groupoid. It's the same characterization. So now, if we are in sets, then we can simplify the definition of a sheaf. So what happened is that we know that En is this fiber product, but En minus 1, but En is also itself a fiber product. And so we can put the two together. And then, okay, this is, maybe I should change color. So this En, I'm replacing it by this fiber product. And then I'm using the fact that in the category of set, when I have a fiber product over, a fiber product over a fiber product, so a two iterated fiber product, I can remove the second base. And in other words, this fiber product here is a sub-object into the product, and taking a further fiber product over this object or over a larger object, it's the same, because this map is a mono. So doing this, I obtain a description of En-1 that only depends on the A's and the B's. So this proves that the data of the E's are completely determined by the A's and B's and the map between them. And a sheaf of sets reduces to the data of a presheaf on the original category J. Because this guy is going to be the limit of this diagram of A's and B's. This is the proof that the enveloping one topos of our zero topos, the frame, is just presheaves with value in sets. And so the same is going to be true for presheaves with value in n groupoids. It's just that now I have to iterate this clever trick with the fiber products. I have to iterate it n+2 times, where k +2 times, where k is the index of the groupoid that I'm considering. And whenever I'm in k groupoid, the ENs are still determined by the A's and B's only. And so the technical reason for this is, oh, I guess I had a slide. Where is it? Oh, no, am I missing a slide here? Sorry, I thought I had one more slide, but I haven't. So, but let me give you another explanation of what's going on in sets. So this reduction in the case of set, it's possible because double loop spaces are trivial in sets. That's the idea. It's a homotopy way to say that. So if I compute a double loop space, this is always trivial. And so if I'm in k groupoid and I compute a k+2 loop space, it's going to be trivial. And so this is the source of the simplification here that reduces the E's to the A and B's. But of course, this doesn't work for k equal infinity, because this kind of rewriting using iterated fiber product never stops now. And so for k groupoids, we can prove that the k envelope, the k topos envelope, is still presheaves into k groupoid, but this is going to fail at infinity. And so to prove that this fails at infinity, this is where we use the existence of an infinitely connected object. So here is the idea that that should be sorry, that should be an f up. So f is our frame. Here, and so we know that the infinity topos envelope is going to be a localization of presheaves over the frame. That's the general construction that I explained at the very beginning. So those guys, they're going to be those presheaves satisfying the sheaf condition. And so I can consider the sheafification of this diagram where I use the spheres. And this is the counterexample, which is infinitely connected in this topos. So let's see. So we need to prove that the sheafification is not terminal, and then we need to see that the sheafification of the truncation is going to be terminal. So let's do that. So how do I sheafify? As it happens, sheafification is very simple because the sheaf condition is just having pullbacks here. And so the sheafification operator is going to be very simple. It's going to consist into shifting left the diagram, meaning forgetting this bit, and then taking a loop space. And so here is the first step of sheafification of my diagram. Now we have omega S1 instead of S0, omega S2 instead of S1, etc. And so if we sheafify again, we have omega S2, etc. And in the end, the sheafification is omega infinity, sigma infinity of S0, of S1, etc. And those spaces, we know them to be non-trivial because they are the stable homotopy of spheres. And so this proves that the sheafification of our object is not the terminal sheaf. So it's not a contractible object in the envelope. And this is, in fact, an example of the colimit of the Yoneda diagram. So this is what we get. And now we need to prove that this is infinitely connected. So let's have a look at the truncation. So for this, we use the fact that the truncation of a sheaf is the sheafification of the truncation. And if we take the P1 truncation of our diagram, we're going to keep S0, we're going to keep S1, but everything higher than S2 is going to become contractible. And so if I apply my sheafification procedure to this guy in 2 steps, I get a contractible guy. And so all the truncation of our object are going to be trivial. And so this is the proof that there exists an infinity connected object in the envelope of this guy, and which secretly is S infinity in a sense. So that's why it's infinitely connected, because it's infinity, whatever it is, it has to be infinity connected. But it's not contractible. And so the envelope, not being hypercomplete, cannot be a presheaf category. And that's it. This time I'm really done.
Very nice. So maybe we can clap again. So let's take another round of questions. I should look at. Are there any questions?
So let me make a comment.
Oh yes, please.
To answer Claudia's second question. Let me go back to the too many drawings. So if I look at the J category, so first of all, the intuition of Chaitanya, I think, was correct. Meaning somehow this category, it looks like it has a contractible shape, but somehow it doesn't. And that's kind of the obstruction, meaning its universal shape, which is the colimit of the diagram in the envelope, is not contractible. And so that's not enough, but that gives an intuitive idea on why something could fail. So I'm not expecting such a situation to happen in nice combinatorial categories like the theta n or these kind of things.
I mean,
because there's too many maps between the objects. And so in the end, the shape is contractible for real.
But what about other things you often like to take sheaves on? I mean, you know, more algebraic flavors, commutative algebras, or, you know, even fancy.
Ooh, so, well, yeah. So, but usually algebraic theories are very nicely presented by means of Lex categories.
I see.
And so there's not going to be any problem for that, unless you get interested in the so-called flat algebras, which are presheaved over the Liouville theory. So it's not exactly the enveloping topos of the Liouville theory. And for those, I have no idea.
Or what about things like, I don't know, compactly generated Hausdorff spaces or manifolds?
Good question. Good questions. They are definitely not Lex category. It's bizarre. It's not easy to find a Lex category that would present the same kind of sheaves. So that's a very good question, whether the category of manifold is good. Yeah, well, that's an exercise. I don't know. I haven't tried. Yeah, I didn't thought of manifolds.
It's probably more like a paper rather than an exercise.
Well, no, I think, I mean, manifolds can be built very easily. So it's patching along open inclusions. Open inclusions are monos. So it looks like the criteria that I have could be applied, but so that's why I'm thinking it's an exercise, but we might have some surprises.
The floor is open to more questions.
Do you think you could combine your argument for G sets and your argument for simplicial sets to get an argument for, say, generalized Reedy categories?
I don't know what a generalized Reedy category is.
Like the Reedy category, but with non-trivial automorphism.
I know what they are supposed to be, but I could never understand the definition. So
basically, you say you have non-trivial automorphisms, but also a notion of set.
I have no idea. That's a good question, because they are very useful to do a homotopy theory. So it would be nice if this was the case for any Reedy category or a generalized Reedy in some kind of sense. I agree. Yeah, but I didn't look at that at all.
You could start with the category of trees and see how it looks.
Oh, I'm too afraid of trees. I'm already afraid of simplices, so trees. Ugh.
Well, I always had a feeling that simplicial sets were good, but I didn't know the technical meaning of it.
So the technical word that I'm using in my notes is not good. Good is just for the purpose of the talk. It's hyperacyclic, because it means that they behave nicely with respect to the hypercompletion. So simplicial sets are hyperacyclic.
How about hyperaspherical?
Same thing. Yeah, agreed. Yeah, I would be okay with that. Yeah.
Any other questions?